Good afternoon and welcome to today's webcast. Our topic, State-of-the-Art Tools for Signal Integrity and Power Integrity Analysis, sponsored by Keysight Technologies, formerly Agilent's Electronic Measurement Group. I'm Chris DiMartino, editor with Penton. Let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. To maximize the slide presentation window, press the small green button at the top right corner of the slide window. We welcome your questions during today's event. Just type your question into the question window on the side of your screen and then hit the submit button. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. Please also be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You will be notified by email when the archive is available. You may also download a PDF copy of the slides by clicking the green folder icon in the toolbar beneath the slides. Let me now introduce today's speakers. Stephen Slater is a product manager for Keysight ESOF EDA's high-speed digital simulation solutions based in Santa Rosa, California. Prior to his current responsibilities, Stephen was an application engineer for DSP and communication systems design for Keysight and Agilent Technologies in the United Kingdom. Stephen holds a bachelor's in engineering in microelectronics and a bachelor in science in information technology, both from Griffith University, Australia. Heidi Barnes is a senior application engineer for high-speed digital applications in Keysight ESOF EDA. Her recent activities include the application of electromagnetic, transient, and channel simulators to solve the challenges of high-speed SerDes and parallel bus communication links. Past experience includes 6 years in signal integrity for ATE test fixtures for Verigy, an Inventest group, 6 years in RF microwave microcircuit packaging for Agilent Technologies, and 10 years with NASA in the aerospace industry. Heidi graduated from the California Institute of Technology in 1986 with a bachelor's degree in electrical engineering. She has been with Keysight EDA since 2012. Now let me turn things over to our presenters. Stephen, the floor is yours.
Thank you very much, and welcome everybody. Thank you for joining us today. ADS 2016 was released in January of this year, and it was a really big release for SI and PI technologies. What we're going to do today is we're going to take you on a tour of some of the challenges that our customers see, and as well as the technologies and methodologies that have evolved to address those challenges. But before we get started, what I'd like to do is make a brief mention of anybody who might be considering writing a technical paper or article. We now have a distinguished author program, so what you can do is log on and fill in the details, and we just want to acknowledge your work. So thank you. The next thing is, if you'd like to have the printed format of much of the material which we're going to be presenting today, you'll find that there's an SIPI resources link that you can go to, where you'll be able to download. This is a technical overview document with commentary. The agenda for today, as I mentioned, is going to be a tour of technologies and methodologies that a high-speed digital designer needs. Firstly, what we're going to do is have a look at the challenges of increasing speeds and complexity. So we have a case study here, which is the KCU 105 evaluation board, which is provided by Xilinx. It's a Kintex UltraScale FPGA, and you see some of the fast interfaces that are on this particular board. In black, I've also got some of the top rate of the particular standards, which may not be particularly on this board, but we can see things like PCIe Express up to 16 gigabit per second, HDMI 2.1, 12 gigabit per second. definitely we're moving faster and faster, and also the complexity of the boards that are being designed is increasing. So that means denser routing. It also means that the layer counts of these boards are very high. This particular one is 16 layers in total. And some of the signal integrity and power integrity challenges that we see, I've sort of split them here left and right. So signal integrity challenges on the left. I won't talk about every single one, but I might pick out a few here just to talk about. What we see for some of these standards is that it's a closed die spec at the input to the receiver. Now, in simulation, what makes it difficult is that such small wavelengths, if we're going to get an accurate simulation to measurement comparison, we need to make sure that our EM simulations capture all of the small features of the board, including all of the transitions onto vias and the coupling between vias correctly. It's important to get those right if we're going to get the high frequency accuracy that we need. The other thing we need to be very careful of is the signal return current. Now, for power integrity, many of these are very similar. We've got the case it's very densely routed. That means there's lots of vias, and the clearances for those vias mean that the power delivery network is no longer one solid plane. It starts to resemble Swiss cheese. And that means that designing a power delivery network to have a flat frequency response and also to deliver the right amount of power to the right IC can be very tricky. And simulation tools are very important to be able to simulate these aspects. Now, another anecdote that a customer shared with me was the case where they were designing for their ASIC, and they put it onto a board. They required to set so many decaps around it, but there was actually physically not enough real estate underneath the chip to locate all of the decoupling capacitors. So their layout engineer went and sprinkled some of the remaining decaps around the rest of the board, hoping that that would suffice. But in truth, the power delivery network's response depends very much on the layout and the inductance of that distributed layout, just as much as it does on the decap value. So what we're trying to do with simulation is to design for an optimally flat PDN. Okay. So those two items are very closely coupled. Typically, we see that we have design groups that may focus on SI and design groups that may focus on PI, but ultimately it's very much interrelated. In ADS 2016, we've launched two new technologies. One is SI Pro and the other is PI Pro, and they all exist inside one common environment. It's a three-dimensional environment, so you can view the nets of interest. You then set up your ports for simulation, and the nets that you've selected are the ones that will become meshed. Those are together with the ground and power planes that you might have selected to add to the simulation. Now, what's special about SI Pro is it's actually a new EM technology. So we call it a composite EM. This means it's a composite of two different techniques. One is finite element method, and one is planar EM, both of which we have a lot of expert domain knowledge on. And what happens is that by combining the two technologies, it means that we actually get the best of both. So we get accuracy at high frequency approaching that of full wave finite element method, but with a speed that approaches other more hybrid simulators. PI Pro, by contrast, is actually a suite of different solvers. So it exists within that same environment, but there's a DC IR drop solver, there's an AC PDN impedance solver, and a power plane resonance solver. And we're going to see these in detail in a little bit further, a little bit later on. But the fundamental message is that with ADS 2016, we have the ability to take your design all the way from whiteboard to test board. So we can take in, start with a pre-layout design, then we can go and go out with a set of constraints. We can the board will be designed in an enterprise board tool, import that back into ADS, perform EM simulation, check the EM model for its performance. Is it good enough to be able to be used in our channel simulations? And then press one button, which will generate the schematic, such that in our original pre-layout design we can remove the channel and replace with a new EM model. So what we're going to do is we're going to pop in and discuss a little bit more detail about what is channel simulation technology and why do we need it. So the motivation for using channel simulation is the case that in our design, we'd class this as being a pre-layout design. We've got a transmitter and we may have a receiver. The transmitter itself has some forms of equalization, so we have de-emphasis and pre-emphasis. On the receiver, we also have equalization as well. And then there's many design decisions that we can make about what goes into the channel. We can vary things like widths and spacings of lines. We can try different connectors. And we can look at different EM models of packages. Essentially what we're trying to do is we're trying to see whether or not we can have an open eye at the output of the receiver. Now, if we tried to simulate all of this with a transient simulator, well, firstly, we'd be down at transistor level simulating the logic blocks for the equalization. And it's just way too many bits need to be processed before we get a decent eye diagram, a representative eye diagram. Also, we need to be able to simulate down to really low bit error rates to be sure that we still have an open eye, even down 1e to the minus 16 or further. And this is where channel simulation came about. So channel simulation now is it's a mature technology. It's been in the market for between sort of 10 and 20 years. Originally, we have a bit-by-bit channel simulation mode, which is the most accurate solution. The way that it works is it has a look at the channel that we have, computes the impulse response from it, and then taking a bit stream, we convolve that with the impulse response, and we get what is a single bit response. And then, knowing that the channel is linear and time invariant, we can overlay the different bit responses from a particular bit pattern, and then sum them together. That's what we call superposition. Now, this means that we are able to handle linear, let's say analog components like the IBIS model, linear time invariant channel, but then for the transmitter and receiver, those are nonlinear time varying, and those are handled with IBIS AMI models. On the bottom, we see a different mode. This is statistical mode, and instead, what this does is it starts with that same impulse response, but now it takes the statistical properties of the bit stream and applies it to the impulse response of the channel. So it builds up a statistical eye based on the probabilities of the transitions from low to high and high to low. Now, the differences here is that the statistical mode is very, very fast. It can get you down to really low bit error rates in seconds. Bit-by-bit mode can extrapolate down to those low bit error rates. But the statistical mode assumes that the transmitter equalization is fixed and the receiver equalization is fixed. So no time-varying natures are captured. Okay, but IBIS AMI and channel simulation enables us to do some pretty complex things. So in a modern board, such as a server, we've got to get a signal from one side of the board all the way to the other side, and these boards can be on the order of sort of 20 inches long. The signal is way too attenuated by the time it would get to the receiver to be recovered, so we use a repeater in the middle, a repeater or retimer. And this can recover the signal and then transmit again. And we can set these up in a single channel simulation. Another thing that's important is, in channel simulation, the treatment of S parameters. Now, it doesn't matter where you get your S parameter from, whether from an EM model or from measurement. It's simply the case that it's going to be band-limited data. So it's got a start frequency and some stop frequency. Now, if you use that S parameter data directly in a channel simulation, what would happen is that the band-limited data gets converted into a response, and that time domain response happens to be non-causal. It's got some variation before t equals 0. And this means if we were to compare what we've captured from a scope versus what comes out of, say, a transient or channel simulation, we would see some differences. But what's different about the channel simulation in ADS is the case that we have a patented technique called the RAL method, which means that we take the S parameter data, we look at the time domain response, we enforce causality, and the way it's enforced causality is by way of a Hilbert transform that essentially is going to add additional spectral content such that the time domain response is causal. And we can see by the comparison here that then that means that the reference compared to the transient simulation from that S parameter file comes out exactly on top of each other. And that's a really important thing. So what we're going to do now is we're going to jump into a demo. Now, this particular demo is a video, so if you find that it's not refreshing very fast for you, please let us know in chat. What I've got set up here is a PCI Express 3 channel simulation, so a pre-layout analysis. And I'm clicking on the transmitter, and we see that we get to specify the pre-shoot and de-emphasis here. Within this model, the pre-shoot and de-emphasis is actually set up by way of a variable. So I've not put in a value for it. We're going to go and change that value outside of the component. But this model as well also handles spread spectrum clocking, which is quite important for PCI 3. So we see we've got a channel sim controller. At the moment, we've got 10,000 bits set up. The pre-shoot and de-emphasis setting is being read directly from a file. So let's go and have a look at what that file contains. And you can see there's actually no black magic. It's pretty easy to go and add in new presets. But these are the presets that are taken directly from the PCIe Express, it's the PCI SIG specification. And what we're doing is we're sweeping through the different presets. And we're going to try and find which of those presets is going to give us the most open eye. Now, within our channel, we've got a package model, which is from EM. We've got a transmission line model. We've got via models, which are also from EM, and a connector. The connector is measured data. And then we finally terminate in a receive model. It's an IBIS AMI model, and that's because we've got some equalization inside. So we've got CTLE. We've also got clock data recovery, and we've got decision feedback equalization, and it's adaptive as well. So that means that it's going to simulate and try to find the optimum taps and optimum sampling point. Hitting simulate really drives home the performance of channel simulation. We can see here that we have 10,000 bits in less than 10 seconds. And now we're having a look at the results, and we get our eye density. What we see in the center is an eye contour, and then the red is a timing bathtub curve. You can see here also that I've swept through the different preset index. So these indices are on the bottom, and what we're plotting against is the eye height and eye width. And what we can actually see is that number 4, preset number 4, gives us the best, the highest eye height and width. Now, if I take my cursor over this, these are the individual bit error rate contours, and we see that indeed, yeah, preset 4 does give us, the biggest eye. And the next thing we would do from here is go and put in the mask and make the measurement from that bit error rate contour to the mask. Okay. The other thing we also need to do before we move away is to think about, from the spec, there's channel compliance masks. In this case, we've got the differential return loss, SDD11, and we're just proving to ourselves that our channel does meet that requirement. The other thing about channel simulation, which starts to become very important at very fast frequencies, very high data rates, is the case that the jitter that we expect on our signal, it can't just simply be injected at the receiver, because we have a channel that has a frequency domain response, and the jitter actually has frequency content, which is going to be, attenuated unequally. So in ADS channel simulator, we handle the jitter, very, very accurately indeed. Okay, the next thing we're going to do is we're going to pass over this one. The next thing we're going to do is go pass over to Heidi, and Heidi's going to spend a bit more time talking about S parameters and data mining from them.
Thank you, Stephen. You did a great job of walking us through the channel simulation technology. Now I want to take a closer look at the S parameter behavioral model that you were talking about, and some of the tricks you can do or learn about for using S parameters in your channel simulation. First, when you place an S parameter in your channel, and you're going to use that S parameter, it's very important to make sure that you actually wire it up correctly. And when you place this SnP block into the ADS schematic, you can double-click on it, and you can see here in the upper left that the SnP block allows you to actually view that S parameter and look at making sure that, for instance, your port 1 to port 2 is the through path. You can also create labels for those pins and update your schematic symbol to have those descriptive labels and make sure that you're using that S parameter correctly in your channel. The SnP Schematic Block also has an S parameter checker to check for causality and passivity and make sure that if in the case of a measured S parameter or an EM generated one, that it is actually viable for a time domain channel simulation. Next, one of the other neat tricks about using an S parameter behavioral model, it's a frequency domain's description of the behavior of that channel, including what goes through the channel, the insertion loss, as well as what is reflected. But what is very interesting is mathematically you can convert that to the time domain and look at TDR and TDT, as well as in the case of SERDES channels where there's differential signaling, you can look at that S parameter in terms of single-ended signaling excitation or differential signaling excitation. And up here in the upper right, you can see I have a little reminder of how the S parameters are written in the mixed mode format, where you have in the upper left is the differential in and the differential out. That's the differential signaling. But you also have below that differential in and common out. This is what happens when you get mode conversion, and that common out can cause significant EMI. So a lot of times you want to look at that mixed mode differential in common out signal to see what sort of EMI problems you might have. But these mixed mode S parameters, one can look at them in the frequency domain as differential signals, but you can also look at them in terms of impedance and in terms of near-end crosstalk and far-end crosstalk. So a significant amount of data can be analyzed and a lot of information obtained just from that simple S parameter behavioral model. Now, one of the things that's very unique with simulation tools is the ability to actually look at channel pathology. And within ADS, we have a lot of algorithmic models that you can also put into a channel and create that S parameter behavioral model. With those algorithmic models, it's very easy to change features and see what the response is. Again, we can look at the performance in the frequency domain, TDR, TDT time domain, and we can also put a bit stream through there and look at the statistical eye performance. Let's go ahead and take a look at a good example of what type of channel pathology you might want to do. Here's a simple example of some impedance discontinuities, and we're going to look at a stub impedance discontinuity, which might be typical for a via that is not backdrilled. And we're also going to look at a series impedance discontinuity, which might be typical for a connector going from board to board. And the question is, why is the stub so bad? And if you look on the left here with the eye diagrams, clearly at 25 gigabits per second. The I diagram for the stub impedance discontinuity has a lot more degradation than the I below it for the series impedance discontinuity. If we look at the TDR plot of the impedance discontinuity versus distance into the structure, we realize very quickly that the blue is the smaller impedance discontinuity here, which is the stub, but it did not have as good performance on the I diagram, whereas the series impedance discontinuity is showing a lot more excess capacitance in this case. What we learned very quickly from this simple pathology experiment is that TDR impedance plots can tell us where the problem might be, but it may not necessarily tell us the magnitude. And the reason is, if we look at the stub, there's actually 100% reflection at the bottom of the stub, and that signal comes back and interacts with our forward traveling wave. In the case of the series impedance discontinuity, based on the telegraph equations, there's a smaller percentage based on the delta between those two impedances as to what gets reflected and bounces back and forth in there. Another great example to look at is very simple pathology simulation is how two traces can couple between them and what sort of near-end crosstalk and far-end crosstalk can occur. Down here on the left, you see that we're going to take two identical 12 mil wide traces with a 5 mil gap. So we have these 12 mil traces with a 5 mil gap. We're going to place them on the top of the printed circuit board to create a microstrip transmission line, and we're going to place them into the board, internal, with ground above and below to create a strip line transmission line. The microstrip does not have uniform dielectric around it. The strip line does. When we look at a simple plot of the frequency of the amplitude of the signal going through those traces versus frequency, we see that with microstrip, the blue trace, when we put the signal in on the aggressor side, all of the signal is coupled over to the victim as microstrip far end crosstalk. And so at 6 gigahertz here, we have complete transfer of the signal from the aggressor to the victim, and the far end crosstalk is very high. That shows up in the I diagram at 5 gigabit per second as a lot of degradation in terms of that edge transition. What is very interesting, and if you haven't looked at this before, is in the strip line case, the inductive coupling and the capacitive coupling are canceling, and the far end crosstalk is very low. So when I put the signal in on the aggressor trace, very little, if any, goes over to the adjacent victim trace that's only 5 mils away, and you can see a wide open eye. This simple experiment here in a simulation tool provides a lot of insight into why you might want to route internal strip line transmission lines for low noise applications. With that, we'll turn it back over to Stephen to look at how you can actually generate some of these S-parameter behavioral models with an EM simulation tool for signal integrity.
Thank you very much, Heidi. Okay, so in this demo, we're going to start with the KCU 105 board, and we're going to analyze the DDR4 traces. The first step is actually to get the board into the ADS layout, so we can go and import it. And what's brand new in ADS 2016 is the ability to import the .brd files directly from Cadence Allegro. You just need to have Allegro installed on your machine. It doesn't need to be licensed. And if you've not used ADS layout before, it's actually a very powerful editing tool. So what we're going to do is show you how I can go in and zoom on a particular net. So search for, say, DQ1. We can zoom in, and then say we analyze this trace and realize that the impedances were not correct. Then we could go in and we can make some small changes. We use this like a sandbox. You can see that it's actually overlapped here with another net on a hidden layer. So at the moment we've got lots of vias, but we're only looking at 3 layers turned on. So it gives you this visual feedback if there's something wrong with the layout. Next thing, I've gone and adjusted the width of the trace. So we can see that once we've run an EM analysis, if we found something that we're not happy about, we can go back to the layout and we can try different what-if scenarios. This is SI Pro. This is what the window looks like. You can see that everything is net-based, so I'm going to select this first byte lane of data nets. Because this is a video, you'll see that as I rotate, we get some visual artifacts. That's not a feature of our tool. That's just the video. I try to keep the bandwidth low for so many people on the call today. So we zoom in and have a look at our nets of interest, and then what we can do is we can also use the mouse, taking the mouse over individual objects within the layout, and you see that it tells you exactly what that object is, and you could just click and select objects manually like that from the 3D view. So once we've got the nets that we want to simulate, we add them to an analysis, and what we do is we add the nets we want to analyze as well as the ground or power planes that we might like to also include. We select those nets and we create ports for them. And I'm selecting a few ports here, so they're automatically generated for you by looking where is the closest pin on the ground plane that's closest to my plus terminal, and it will create all of those for you. We go and run our EM simulation, and the next thing that's important to do is go and plot the results. But particularly for DDR, there's so many ports in this design that we want to be able to efficiently filter through the results. And that's what we've got here. So I've filtered by DQ, the data nets, and I've also filtered by U1, so that happens to be the FPGA. So I'm just looking at transmission from that particular port. We can plot crosstalk, but I'm going to save that for later, because the first thing that we want to, the thing that we want to do next is generate a test bench, or generate a sub-circuit from this, and then go and do some more work in the schematic with this EM model. So here's a simulation set up all ready to go. If I push into this component, you'll see what was created by SI Pro, and that schematic inside was generated automatically for us. All of the nets are populated correctly, all the port names are populated correctly, and then now we've got this nice symbol which we can place into the middle of our channel simulation. Now in this instance, we've got ideal transmitters on the left and ideal transmitters on the right, and we run a simulation. And the reason why we just want to start at the moment with ideal transmitters is we want to see how much eye degradation there is just purely caused by the channel. And we can see very easily that DQ2 and DQ6 look to be significantly worse than, say, DQ1 or DQ5. And that might give us some ideas to go in and analyze and find out why. So popping back into SI Pro, what we do is go and have a look at, let's look at DQ2. Let's also plot DQ6. We see there's a little bit of impedance difference between them in multiple places, actually. But then if I plot DQ5, which we can use as our control, we can see that actually it's not that bad compared to DQ5. DQ5 has very little inter-symbol interference on it. So maybe impedance mismatch is not the cause of what we see. So we're still searching. The next thing we could do is maybe have a look at DQ2 and look at crosstalk. So we can right-click and say plot near-end crosstalk. And the next thing it's going to do, we'll plot far-end crosstalk as well, and just see which of those is dominant. Which is actually it's the near-end crosstalk at the higher frequencies, which is worse. We can then go and do the same thing for DQ5. And one thing that starts to become quite clear is that it has a lot less crosstalk on it. It's nearly 10 dB less crosstalk between DQ2, compared to, DQ5. So just for contrast, let's put them back in. And so we found our first insight. So the next thing we can do is say, well, why don't we go and take a marker and place the marker on, that top trace and work out which of these is actually, coupling the most to, to DQ2. So I'm looking at the marker properties, and it tells me it's DQ2 coupling to DQ6 and vice versa. Well, that's interesting. You know, we might have found our smoking gun because it turns out that those happen to be the two worst eye diagrams that we had. So we go back to the geometry and go and have a look and see where DQ2 is and have a look at where DQ6 is. And we can see that actually, yeah, they start very close together. One of them's routed around the other. And if we just have a quick look at the others in that byte lane, we see that they're not very close at all. Now, if we go and have a look at the other end, we see that these two traces don't spend a lot of time running parallel to each other very closely, but they do end again. And it goes to show that a lot of the coupling that's happening is right at those pair of wires at the start and at the end, as well as the metallization on the top. And that's pretty important. I mean, for this design, is it problematic or not? I honestly don't think that it is. I don't think that the degradation is that bad. But at least we've discovered some extra information that we can then go and analyze in more detail later. So that leads in nicely to a discussion about DDR4 and some of the challenges that we see in designing for DDR4. So what is different about DDR4? Well, to start with, it has a reduced voltage level, so 1.2 volts, less voltage swing to work with. And the next thing is because it's much faster, people are designing for 2133 and 2400 at the moment. The fastest commercially available DRAM is an overclocked version of DDR4 for gaming, which is 4133. And the unit interval is much, much smaller than what we've used to designing before. Random jitter and intersymbol interference now eat up a much greater proportion of the unit interval. We could add in additional safety margin, but that is going to lead to over-engineered solutions. So a different solution is JEDEC introduced the concept of a mask test. Now, these mask tests are very similar to what we see in SerDes standards. So we have these in USB 3 and PCI Express. Essentially what we're trying to say is we've got a mask specified at the center of the eye, and the mask is specified at a very low bit error rate. So for when DDR4 originally was proposed and approved, it was 1e to the minus 16 for data. And I've seen a recent version of the document for command address where it's now down to 1e to the minus 18. What we need to do is make sure that our eye diagram stays outside of that mask, because if we don't, then we all can kind of guess at what the outcome might be. The difficulty about this is it's the case that it's it happens very rarely, and if we rebooted the system and ran a memory test, everything would be fine, and we run again, and it fails another indeterminate time from now. So what does it mean for simulation then? Well, the prevention to all of this is to optimize the design for greatest margin to the bit error rate mask. The typical tool that we use, the typical simulator we use for DDR has been Transient, Transient Spice. But just to put things into context, if we're going to be sure that we stay outside of that mask, then we need to process 1e to the 16 bits, and that is a lot of data. So what are different ways that we can do it today? We could do it with dual Dirac extrapolation. That's what they do in the oscilloscopes. The difficulty we have there is that it takes 1 million bits before we can build up a reasonable extrapolation with any degree of confidence. And in SPICE simulation, that's not really possible. The next thing that we could do instead, and this is something that DDR designers have been working with for quite a long time, is to work out what the worst case bit pattern would be. So I bring up the idea of a channel here, and we've got a channel that has 3 slots. So we've got 3 different DIMMs plugged in, and the memory controller is on the far left. It's about 5 inches long. And with that given channel, at a very low speed, we see the impulse response of the channel, and that equates to about the same length as about 2 unit intervals of DDR3 800. So at any point in time, there's 2 bits in flight throughout that channel. When it comes to DDR4 at 2400, we've got 6 bits in flight throughout the channel. So by the time the 7th bit is entering, then the energy from the first bit has pretty much completely left the channel. That's still not too bad because it means there's only 2 to the 6 possible bit combinations, and one of those gives us the worst case bit pattern. But unfortunately, it's not quite as easy as that because we have to consider crosstalk as well. And the impulse response from the crosstalk responses is much longer. And it doesn't really matter how many crosstalk aggressors we consider, the numbers that we're looking at, the number of possible permutations is huge. So that means that worst case bit pattern starts to be very difficult. I mean, we can simulate with Transient for 10,000 bits and see that we've got an extrapolation of our I, and is that good enough? Well, the answer is we can't be sure. If you can't be sure you've caught the worst case bit pattern, then all is for nothing. So what is the final solution? Well, seeing as the bit error rate mask is taken from a SerDes spec, why don't we borrow some simulation technology from the SerDes world? So if we recap back to the statistical eye technique and now consider applying this to DDR simulations, the one thing that needs to change is that channel simulation is for differential signals, and therefore we expect the rising edge and falling edge to be the same. With DDR, it's the case that we've got single-ended signals, with the exception of things like the data strobe, and that means that the rising edge and falling edge actually have a different time constant. So what we've created in ADS is a channel simulator. So it's a parallel DDR bus simulator. It's a statistical technique. It captures all of the crosstalk from each of these components. You can put these individual ideal sources driving an IBUS model, and then going out into the package, the board, and then into the receiver. It'll compute the bit error rate to mask, and then also we can now account for receiver equalization. The typical sort of measurements that you see is that bit error rate eye contour in the center of the eye, and then the measurements to the mask. But because it's fast, then it enables extra usage. So DDR has multiple topologies and multiple different scenarios we need to simulate. If we're simulating in the right direction versus the read direction, then the on-die termination settings need to change. And we can do that very effectively with a batch simulation that's reading all of the configurations from a CSV file. And what we do is we have a look at what's going to give us the worst case, and that will give us feedback. That particular run was the worst, and we can look up what the parameter settings were, and that gives us extra insight into our design. But to round up the discussion on DDR4, we also need to talk about transient simulation, because it's a complementary technology to DDR bus. So while DDR bus is the workhorse, we still need to run some transient simulations to compute things which are more traditional timing measurements, like setup and hold, and flight times, and the different electrical voltage level measurements. Okay. So now we're going to move over into discussing leading edge SerDes standards. So I'm going to pass over to Heidi. Heidi, you might be on mute.
Yes, sorry about that. I caught myself on mute there. So thank you, Stephen. We had a good look there at the parallel bus architecture. So now let's go ahead and take a tour of a serial bus architecture where we have clock data recovery. And one of the things that is hitting the industry now is a revolutionary change in how we do the signaling, and that is with multi-level signaling. And specifically for 100 gigabit Ethernet, the standard actually allows you to choose between non-return to zero, NRZ, or PAM4 with multi-level signaling. The basics of this are NRZ, if you look at it, let's get some terminology correct here. NRZ, for each symbol, has 1 bit of information. In PAM4, we have 4 levels, and each symbol represents 2 bits of information. So 56 gigabit per second NRZ is the same number of bits as 28 gigabaud. Baud means symbols per second. What is very interesting is that the clock rate, or the Nyquist rate, or the clock rate, is for NRZ is twice as fast as that for PAM4. So if your clock rate is faster, is required to be faster for NRZ for the same number of bits of information, then that means that you need to have a wider bandwidth, higher frequency response channel, and this can often cost more money. So let's take how we're going to simulate PAM4 and maybe do a look at a particular pathology. In this case, with PAM4, the industry has found that IBIS AMI provides a lot of ease of use for the end user. The SerDes vendors are successfully bringing these AMI models together with the EDA tools, and it provides for very fast channel simulations, as Stephen was showing us earlier. The IBIS AMI model provides operability between tools. It also provides significant IP protection. The PAM4 models require a lot of equalization in the transmitter and the receiver, because with PAM4 you're dealing with very lossy channels, and so that type of complexity in the equalization would be very difficult to simulate fast in a SPICE type simulation. And so in this case, by putting it in an IBIS AMI model, we can significantly speed up the exploration of the design. And again, this is being adopted widely by for all vendors in the ecosystem of your channel, from IC vendors to component vendors to EDA companies. A quick look at a pathology example for how do you decide if you're sending 56 gigabits of data through a channel. How do you decide whether you want to use NRZ or try the new technology of PAM4 with multi-level? Well, one of the things to think about is not all channels are just material loss. If I increase the loss or the length of a channel, I have typically a smooth degradation of loss versus frequency. And it turns out with NRZ signaling and the sophisticated equalization technologies, it can go quite far. But not all channels are equal. So what happens if you have a connector that maybe the bandwidth dies rapidly after the Nyquist clock rate of the NRZ signal? So in this case, if you look at the spectral content down here on the bottom of PAM4 28 gigabaud, above 20 gigahertz I have very little content. However, for NRZ 56 gigabits per second, I still have a 28 gigahertz clock rate, and I have significant signal there above 20 gigahertz. If I put this through a channel that has a significant loss of signal after the Nyquist rate of the 28 gigabaud clock rate, you see here that the 56 gigabit NRZ signal without any equalization is a very corrupted eye, and the same thing for the PAM4. Both eyes are closed. However, with the 56 gigabits per second needing the wider spectral bandwidth for the channel, there is no possibility of opening that eye up with equalization. However, the PAM4 signal can easily open up the eye, and in this case we are able to get 56 gigabits per second of data through that channel with PAM4, but not with NRZ. So just a quick example of how you can use simulation and explore whether your channel, existing channel, can support more data per second without any upgrades. Now we want to switch gears. As we mentioned, we're taking a tour, and when you're doing your digital signaling, you expect the amplitudes to be precise, but that's actually not true. Power integrity tells us that we can actually have ripple in our power delivery, which equates to ripple in our levels or noise. Very simply, the variation in current in our required for doing our signaling from ones to zeros, or our symbol rates, that variation in current that's occurring in the transistors needs to come through our power delivery network, and that small variation times the impedance of our power delivery network will give us a ripple in amplitude that we end up seeing on our digital signals. So what we find is we want to keep that impedance of the power delivery network down to a minimum impedance, so that when we multiply times the transient currents, we keep our ripple within spec and minimize that ripple. This impedance is called a target impedance. Now, one of the things that we talked about in our webcast in January with Steve Sandler of Picotest was that it's not just important to keep the impedance below the target impedance for your device for the signaling, but also to keep it flat. And one of the reasons that you want to try to keep the impedance flat is that if you have a peak at a single frequency, you might still meet the ripple spec, but in a digital system, you don't exactly know which frequencies are going to be excited. It will be very pattern dependent, and even things as going into sleep mode and coming out of sleep mode for low power operation can cause spectral excitation at quite a variety of frequencies. So if you have a peak in impedance at two frequencies and excite those both at the same time, there is the possibility for a rogue wave. If you keep the impedance versus frequency flat, then you can eliminate the possibility of rogue waves. And essentially, if you read some of the books on power integrity, they will tell you that the minimum amount of capacitors to achieve a flat impedance, or what I say, basically the minimum number of capacitor loading is designing for flat impedance. This flat impedance for minimum capacitors is also maximum stability. So it's actually very advantageous to try to design for flat impedance and not just below the target impedance. Another thing that I want to just mention and was talked is that when designing and optimizing those capacitors and determining at what frequencies you may need to add additional capacitors, it's very important to include the parasitics that are part of the mounting inductance of the vias connecting to those capacitors and the spatial parasitics of the printed circuit board. And here you can see EM simulation that creates an S-parameter behavioral model that allows one to look at the impedance versus frequency with no capacitors, and you can see a high impedance peak there. Or if you load the capacitors, you can drive the impedance down to the desired target level. One other item to mention, and this is the industry is very interested in, they have been working closely with the IBIS Standards Committee to create transmitter and receiver models, IBIS models, that allow, that capture the interaction between the ripple on the power supply and the amplitude ripple coming out on your digital signal. Combining that with an EM simulation that also looks at any adjacent coupling on the printed circuit board can make for a very powerful signal integrity and power integrity co-simulation and look at real-world jitter and noise effects on your actual high-speed digital signals. With that, I would like to remind people that one of the first places to start is with, in terms of power integrity, is to always start with power integrity IR drop. And that will let you know, are you actually at DC, start with DC, are you getting the right voltage to your device? Is it getting the voltage level it needs? And sometimes, if you have a significant amount of IR drop, you may need to add sense lines, or you may need to look at where's the strategic place to put the sense line so that you provide optimum power to multiple sinks or devices using the same VRM supply. With that, I would like to turn it back over to Stephen to do a great demo of the ADS Power Integrity PI Pro tool that provides these EM simulations and the distributed parasitics.
Thank you very much, Heidi. So just remember that if the video freezes up for you, you can hit F5 to refresh your console. So we'll just go to the very last demo here today, so we're running out of time. But we're looking at one particular net. It's the 5-volt net that runs around the outside of the KCU 105 board. And what we're showing here is where the sinks and VRMs are located on that board. A DC simulation, DC IR drop, is very, very fast indeed. So we're looking at 30 seconds for this particular simulation for over 1 million cells. And in fact, if we chose not to include the ground plane in the simulation, it would be even faster, less than 10 seconds. We have a look at the DC results overview here. And given what we set our VRM up to, the particular voltage and its parasitics, as well as the current requirements of the sinks, it goes and now and tells us the DC current that we're seeing through each of the vias and also at each of the pins. So if we select particular vias that we want to look at, it shows you whereabouts exactly in the geometry they are. So we can go in and have a look and see indeed that these two here are capturing, it's 120 milliamps and 56 milliamps for those two particular vias. The next thing we'd like to do with the simulation results is have a look at the voltage distribution. So we first go and turn it on and show just hiding the geometry so we can just have a look. And I take my little field reader, and it's 5 volts here, and 4.979 there, and 4.969 here, showing you that we definitely have lost some of the voltage by the time it gets to where it's needed. Now, because we did simulate with the ground planes in this simulation, I can flip to the ground plane on different layers. And this one, we see that actually, yeah, there is different potential depending on where we are in the ground plane. So we had 700 microvolts right at the center. That's the closest to ground. And then all the way over in the far corner, it's 1.1 millivolts. So there definitely is, a slight, resistance between those 2 points. The next thing we might look at is current density. And we zoom in and have a look, and you can see the arrows that show you the direction of the current is taking. And also we see where the current is grouping together, and the areas that we would go and have a look at first and foremost if we were out of spec would be these areas where it's highlighted and lit up, and maybe make some design decisions about making that particular piece of trace a little bit wider in that point, or maybe moving one of the vias. Once we're done with the DC, we then copy through to the AC simulation, and we can do our PDN impedance plot, adding in individual models. In the interest of time, though, I'm going to close up. And we wanted to summarize by saying that Keysight is, world's premier design and test organization. We've got worldwide technical support coverage, and we have many players who sit on the board of directors for many of the high-speed digital standards. So that means that with Keysight, you always have someone to call who has deep insights on your particular design challenges. Someone that we can ask for questions on the standard, and with that, we'd like to thank you very much for listening today and pass it over to questions.
Thank you. Well, that concludes today's presentation. On behalf of Electronic Design, I'd like to thank you for joining the webcast today. Thank you to Keysight Technologies for sponsoring this event for us today. Enjoy the remainder of your day.